Good afternoon everybody. This is the course on basic machine tools and metal cutting principle, and today we have chosen to have discussion on cutting tool geometry and chip formation mechanism. Machining, the classical definition, it is a process by which objective of definite shape, size, finish can be produced by removing extra material from a layer with the help of a wedge shaped device which is called the cutting tool. So, that we all understand, that is the classical definition of machining. Now, if we go to the next one, we understand requirements of machining. That means, what are those elements working around this machining process. We see machine tool, workpiece, fixture, cutting tool, then the environment, and finally the machining parameters, which are namely velocity, feed and depth of cut. This we all know. Now comes the next one. What is the outcome of this machining? We put so much of effort, but what is the ultimate result? The result is that we must get one product of definite accuracy in shape and size, also the surface finish, and in the process we have chip formation. That means, excess material is removed in the form of chip, but along with this few things are associated, that is development of the cutting force, rise of cutting temperature, that also we cannot avoid, and finally it is the growth of wear on the cutting tool that limits the service life of the tool, and that is the limit of the machining process. Somewhere we have to stop. Now, here we find the significance of the cutting tool. Now, here the cutting tool plays a role, and this is a sharp tool, hard tool with which material is being removed. Now, here we find cutting tool means there are two components. One is the material and another is the geometry of the tool. Both are equally important, and if we see, material means resistance to brittle fracture, that is one of the requirement, and then we have resistance to plastic deformation and resistance to wear. And if we consider the geometry, it immediately we understand, even without going much detail into the tool, rake angle. Number 2 is clearance angle, and 3 cutting edge angles, and finally the nose radius. These 4 geometrical parameters decides how this tool is going to perform given the situation, I mean the work material, cutting conditions, continuous or interrupted cutting and so on. So, the cutting tool has to be equipped with, on one side with the material and on the other side with its geometry. Then comes, if we follow here various elements of the cutting edge. Number 1, principal cutting edge. 2, that is minor or auxiliary cutting edge. Number 3, rake surface. 4, principal flank or clearance surface. 5 is auxiliary flank. 6 is tool nose, and 7 is of course the tool base, and finally it is the shank of the tool where we do the bolting for fixing. So, these are the various elements of the cutting tool. Now comes very important thing, how do we designate the cutting tool, or how can we identify the various features of the tool, how one tool is different from the other. So, there are standard ways of defining the specification of the cutting tool, and what we can see here, that at least it is as per the recommendation of ISO, International Standard Organization. We have clearly 2 systems, tool in hand, and on the right hand side I have also shown, that is the tool in hand and tool in use. Now, here we can see that it refers to a cutting tool when the tool is static tool, it is not being used, and on the parallelly we can see a tool which is in use, in actual operation. So, side by side these are the 2 ways of defining the tool geometry. Then we have the tool, how we define it. It is defined in relation to the base of the tool, that means the plane on which the whole thing is resting, and in this case it is defined in relation to the actual direction of the cutting velocity. I mean the resultant cutting velocity and also the direction of feed. You know, these are the two parameters, rate monitoring parameters, cutting speed and the feed. So, their direction finally decides what is the working angles. And where we use this tool in hand system, this is only used for grinding or sharpening the tool. It is a fresh one, or you need resharpening after it develops some wear. So, this is the way we can find a tool in hand and a tool in use. Now, friend, here we go straight to the geometry of a single point turning tool. Let us limit our discussion here, because this is very fundamental and one has to understand it in clear terms. And here we have on the left hand side, it is the machine reference system, and on this side we have a tool reference system. So, there is a difference, and this is actually also known as ASA system. It is popular in North America, and ORS system, this is the continental. Actually it was the German standard later, which was known as orthogonal rake system. So, one is North American, another is continental. So, here friend, to define the cutting tool, first of all we have to define the planes, because simple reason that we have rake and flank, these are the plane. So, if we like to measure the angle of the rake surface, then we must define the plane on which this angle or the slope is measured. So, we have to define the plane of references on which we are going to measure. Now, here we also find that an observation shortcomings, that geometries are independent of the position of the cutting edge, because the cutting edge is the most important element which does the chip removal. But in this case what we see that all the planes, in this case we have this noting, all the planes are defined in terms of position of the cutting edge. So, we have two different thing, one is related to the position of the cutting edge and one is related to the configuration of a machine tool where this cutting tool is going to be used. So, these are the two things one can figure out the difference. And say for example lathe, in a lathe we can define that we have two clear direction. One is called the axis of the lathe, that means the axis of the spindle or the lead screw. Another is the transverse axis where the tool moves in the radial direction. So, we know what is meant by x means the longitudinal axis and y means the radial direction. So, this is something which we like to show here. So, we find planes and angles in ASA system. Just now I have shown ASA system and ORS system. Now, we focus our attention more in detail in ASA system. So, what are those planes of reference? Reference plane, that is pi r. Friend, we use these notations. Pi means the plane and r suffix means the reference plane. And if it is tool in hand, obviously that is the base of the tool, And then we have machine longitudinal plane. Just now I have mentioned it is the plane which is perpendicular to this floor of the laboratory or the workshop on which you have the machine tool, and then you erect this longitudinal plane along x axis and it is perpendicular to this reference plane. Similarly, we have pi y, that is the machine transverse plane, and this machine transverse plane, it is also perpendicular to the reference plane. It is an upright plane, but it is now aligned with the y axis, that means in the radial direction or the cross feed direction. And accordingly few angles are immediately defined, and these are side rake, back rake, side clearance, back clearance, side cutting edge angle, and end cutting edge angle. Now, let us have a quick look. Let me draw a sketch to show what does it mean if we have a cutting tool like this. ফোন নিচে অফ করা আছে Okay friend, so this is the top view of the cutting tool, and here what we understand, this is the principal cutting edge and auxiliary cutting edge. Okay. Now, one thing perhaps would be a good illustration if we use this clearly here. So, we draw this sketch to know about these various elements of the cutting tool. Okay. Let us identify various elements of the cutting tool. This one, this is called the principal cutting edge or the side cutting edge. This side, that is called the end cutting edge or auxiliary cutting edge. This surface, this is rake. This surface, this is called the principal flank. This side, that is the auxiliary flank. And this corner that is called the tool nose, where everything meets. So, all the elements are meeting here. So, this is the auxiliary flank, and this portion, that is the shank, where we bolt the this tool with the tool post. So, friend, these are the various elements of this cutting tool, and with reference to this one, we go back here and immediately you can recognize that is the top view of the tool. Suppose I am the lathe operator. So, in front of me the tool, if you view from the top, it will look like that. So, this becomes the principal cutting edge or the side cutting edge. This is the auxiliary cutting edge, that is the rake surface, and here perhaps we can put some dotted line to show that these are the flank surface. So, these are the two flank surface which we cannot see, and that is the top view. Now, our job would be to visualize various angles, means rake angle, side rake, back rake, side clearance, back clearance, side cutting edge angle, and end cutting edge angle. How do we show? Let us try. On this main cutting edge, just you consider one point. This point can be very close to the nose or very close to the shank. It is not important, it is independent, and through this you have to draw two lines. It means that through this you are passing YY plane. That means it is like a saw. With this saw, which is held in the YY plane, you are cutting the body of the tool. This is one exercise. You can do one more, and in this case you have to draw one more line, and which will pass through the same point, and this is parallel to XX. That means according to this statement, this is YY plane and this is the XX plane. XX plane. It means this is actually, we call it pi x. This XX plane is nothing but pi x, means the machine longitudinal plane. And what I have drawn with this blue line, that is YY plane, means it is the machine transverse plane. These are the two sectioning plane, means it is almost like two saw which are set at right angle, and you cut the tool and you take the section. Now, if we are conversant with the sectional drawing, then what we see, we can have the section of this on the XX plane, because if I just revolve this section. This is the fundamental principle of sectional projection. So, from this what we get? We get a shape of the wedge, and another thing here, if I hold this pen this way, on the top view, that is going to be the z direction. So, here this is the z direction, it is the revolved section. Following the same logic, we can repeat the same process on this side, and we can get another sectional projection, and it is fundamentally an wedge. And since it is section, let us put this section mark. Here too we have to put section, and following this what we achieve? If you look carefully, this line that shows the trace of the rake, and this line that shows the trace of the flank. So, that is the rake and that is the flank. Similarly, this is the rake and this is the flank. Now, where this sectional view is projected, our immediate answer would be it is on the machine longitudinal plane. That means the whole entire view which I am encircling, that is drawn on this x plane, and you revolve it. Similarly, this is also drawn on the y plane, that means machine transverse plane. So, finally, we are left with two figures 1 and 2. With this we can show what is the rake angle and what is the clearance angle. Now, here friend, this will be gamma x, because it is on the x plane. Gamma means rake angle. I follow all through. Gamma stands for rake, alpha stands for clear. There may be other convention, but for the moment we follow this convention. Then this becomes alpha x. Similarly, on this side this becomes gamma y and this becomes alpha y. So, we can define the geometry of the tool, at least the rake and clearance, by this choosing these two planes, and these two planes are nothing but machine reference planes, one in the x direction and another on the along the y direction. And friend, to remind you, these two planes are perpendicular to the reference plane, and in tool in hand system, this is the base of the tool or the platform on which the machine tool has been installed. So, this way we can find out the gamma x, gamma y, alpha x and alpha y. So, this is the way we can define. Now, what are the things to be remains to be done? We have to show, if you have noted, these things were displayed, phi s and phi e. What is phi s? Now, parallel to this y axis, you just draw one line, and then you can look carefully the angle what I am showing here, this included angle, that is phi s. So, it is very simple. You have the side cutting edge, and then you draw one line parallel to this y axis. So, this is the orientation of this side cutting edge with respect to this y plane. Now, where is phi e? What is mean by end cutting edge angle? It is also not difficult to show. You draw one line through this tool tip or somewhere here, no problem, and this line should be parallel to x plane. So, to show phi s, you have to draw one line parallel to y, and to show phi e, you have to draw one line parallel to x, and this included angle, that is phi e. And where is our nose radius? Friend, this is the nose. It is a sharp point, but you can put a radius in here, you can put a radius, and if you put a radius like this, simply you show it with this point that R. It is obviously in inch, 1/16 inch, 132, 1/8, whatever may be the value you assign there, and with all this we come to the completion of specifying this cutting tool in terms of ASA system. So, we have to follow one order, and that order is already set. It is not what I have created, but it is the order already standardized. So, you have to write gamma y, gamma x, alpha y, alpha x, phi e, phi s and R in inch. So, that is the way you specify the cutting tool in ASA system. Now, if we like to go to the ORS or tool reference system, what we do very interesting, this x and y it appears like a cross, it is like a plus sign which is rigidly hinged here. That means, this plus can be rotated about the z axis. So, it is a plus sign which you can rotate. Now, if you just consider that if you rotate the whole setup, that means this x and y that is a cross which is rigidly hinged here, and you rotate it through phi s, what is going to happen to this plane, orientation of the plane? Let us have a quick look. So, friend, according to this, what we get here, we draw the same cutting tool, here, and as I have just now mentioned that this y plane will be now aligned with this cutting edge. This is now your y plane. You can have a quick comparison. This was the y plane, and now I have rotated it through phi s. So, it is just the rotation through phi s, you get y plane. Now, where will be the location of this x plane? Yes, it is the same point, I have not changed the point. So, you just drop one right angle. So, this becomes your x plane. So, this is your x plane and that is your y plane. So, with that what you get? You get from ASA to ORS. ORS means it is orthogonal rake system, or we call it tool reference system. Friend, one interesting thing, as I have said at the beginning of the lecture, that alpha, this gamma y, gamma x, whatever we have shown, that is independent of the location of the cutting edge. So, cutting has this cutting action cannot be judged by looking at gamma y, gamma x. These are independent. This is fixed according to the configuration of the machine. But here we do not consider the machine, we consider the cutting edge. This edge, it can be oriented like this, it can be oriented like this. This is the orientation of the cutting edge, and accordingly you keep this line y plane and x plane becomes perpendicular. So, in summary, it is nothing but this x y plane, that system you rotate through phi s and you get this new system, and with this new system we call this y plane, we have to give one new name, we call it either cutting plane or tangential plane, and we put as pi c, symbol pi c. Pi means the plane and c means the cutting plane. Now, here x is always at right angle to y. So, this x it is no longer the machine longitudinal plane. Machine longitudinal plane would have been like this, but now it is rotated like this. So, it is now the orthogonal plane. Why? It is now orthogonal to this cutting edge. So, friend, this is also we call it orthogonal plane. So, we have now in tool reference system, we have cutting plane and orthogonal plane, and both are also at right angle to the reference plane. And to get a cross sectional view, what we have to show? You just draw one line here and you get this line the way we have visualized gamma x, alpha x and gamma y, alpha y. So, this is a cross section, and that is the z direction. Z direction has not changed. So, it is still the vertical direction, it is the vertical direction. So, here it is on the orthogonal plane. So, this whole picture it is taken on this orthogonal plane, because now the saw moves like this and you cut it and take that section. So, this included angle that becomes gamma O, and this angle that becomes alpha O. So, we understand orthogonal rake and orthogonal clearance. How do we define? It is the inclination, angle of inclination of the rake surface with respect to the reference plane. This is the base of the tool. So, it is parallel, this plane is also parallel to the base of the tool. So, it is the angle of inclination of the rake surface with respect to the reference plane, and it is measured on orthogonal plane. So, important term here in the entire statement is the plane on which you are visualizing or measuring those angles, namely the rake angle and the clearance angle. So, these are the two things to be taken into consideration, and we have to remember this. So, that means angles are measured in ASS system in machine longitudinal plane, in machine transverse plane, and when it is orthogonal system, now we are discussing ORS, and originally it was ASA. This was ASA, and now we are discussing on ORS. So, in ORS at least we know alpha O and gamma O. Now, we go to an important thing, that is actually the inclination angle of this cutting edge. So, inclination angle of this cutting edge means you have to have your view from this side. From this side you have to have your view from this side, looking from this side, and take the view on a screen, or you look, you place here this YY plane, maybe it is like a perspex, it is a transparent plane, and through that you can visualize this cutting edge. And when you visualize this cutting edge, your drawing maybe something of this sort. Let me have a quick explanation. So, this is what we have already drawn, and if you have the drawing from this side, dotted line means the flank surface, it is obvious. Now, from this side you have to draw these lines, and it is the projection. So, it will be some sort of this thing. This is the cutting tool. That means it is not a section, because this case this YY what I have shown now, this is now it is not YY as I have sent. This Y is replaced by the term C. YY is replaced by the term C, and when it is the orthogonal plane, definitely we should replace x by O. So, my submission is that because of this rotation through an angle phi s, pi x becomes pi O, obviously x should be replaced by O. Similarly, machine transverse plane, which was YY or pi y, that should be replaced by C. So, this is pi c and this is pi O. Now, getting back to this, so this picture in one language, one line, this picture what I am showing here, that is taken on the cutting plane or the tangential plane, and on that you can see the orientation of the cutting edge. So, this is the cutting edge, means this point means this point, and this zone means this zone. So, this is actually your cutting edge, principal cutting edge, and this is the line which is drawn through this tip of the tool, and this line is parallel to the base of the tool, and this is actually the reference plane. So, where is the angle of or inclination of the cutting edge? This is the cutting edge, this is the cutting edge, this is the cutting edge, and this is the horizontal line. So, this included angle, that is known as inclination angle of the cutting edge. It is the angle of inclination of the cutting edge in with respect to the reference plane. This is the first part of the statement, and it is measured on the cutting plane or tangential plane. So, this way we define lambda. So, friend, here we have defined what we have just now concluded, gamma O, and here we have alpha O, and here we define alpha lambda, and two things remains to be done in according to this drawing. So, here this is the principal cutting edge, which is known as side cutting edge in ASS system. This angle is phi. Please note the location of phi and phi s. Similarly, this is the auxiliary cutting edge. So, this angle is known as phi 1. So, one thing we can observe that this phi of ORS system is equal to nothing but 90 minus phi s, and phi s is referred to ASS system. So, this side is phi s and phi 1 is in magnitude, it is phi e. In ORS system we call it auxiliary cutting edge, and in ASS system we call it end cutting edge. So, this is phi 1 and phi e, both the things are defined. However, advantage of this ORS system, one is definitely here the cutting edge is included. So, that means you set the planes in a manner that the planes are referred to the cutting edge. So, the plane passes through the cutting edge and one plane is perpendicular to this cutting edge. So, it has some sense because cutting action is taking place in a direction normal to this cutting edge, because the chip flows in this direction. So, that way it is significant. And one more thing is important here, that we have to also consider the auxiliary cutting edge, because the clearance of this auxiliary cutting edge in ASS system that has not been taken care of, but here we have to take care of this auxiliary cutting edge, because auxiliary cutting edge is also the auxiliary flank. I mean that clearance is important, in that if you do not provide the clearance here, this will simply rub over the finished surface and that may spoil. So, if that should be the case, then we have to consider one plane like this, what I am drawing with this blue line. So, this is another plane, and this plane we call it pi o dash. So, friend, you should not have any ambiguity in defining pi o and pi o dash. Getting back to this previous figure, this is pi o, that means orthogonal plane for the principal cutting edge, which I have shown with this red one, and here the blue one which I have shown here, that is the orthogonal plane for the auxiliary cutting edge. So, you have in one diagram, perhaps I try to show, this is the auxiliary orthogonal plane for the principal cutting edge, and if you put another plane which are all sectioning plane this way. So, this is a sawing plane orthogonal for the main cutting edge, and this is another orthogonal plane for the auxiliary cutting edge. Now, with this, what we can show here, an important parameter. So, if I extend this line, then you can show here again it is the same wedge. So, friend, basically when we show the rake and clearance, we get the shape of the wedge, which is finally the cutting tool. So, in this case what we get this thing, and we put this hatch mark here to show the cutting, and this is the z direction, as we have shown this is the z direction. Similarly, here we have this z direction, this is the z direction, and this is one plane parallel to the base of the tool. So, this angle is not important because we cannot specify, it is already set in the tool. So, we cannot consider it independently, but what can be assigned independently on this auxiliary side, friend, this is alpha O dash, very important parameter and which is not there in the ASA system. So, let us summarize in ORS system how do we specify the thing. How do we specify the thing? That means it is lambda. I have explained gamma O, alpha O dash, phi 1, phi and r in millimeter. So, this is ORS. So, now you can see the difference between these two originally what we have shown. So, it is gamma y, gamma x, alpha y, and here it is the replacement by this lambda, gamma O. These are very much an integral part of the cutting edge. That is why it is significant. Not only that, in this case you do not have any information on the auxiliary flank or the clearance, but here that is provided alpha O dash. So, these are the two things we have discussed and we have to consider these two and their significance. So, these are the planes of reference we have considered, and if we now go here in this case, so friend, already I have discussed. So, it is just recapitulation. I have defined reference plane, I have defined pi c, cutting plane, orthogonal plane, inclination angle of the cutting edge, orthogonal clearance rake, orthogonal rake, auxiliary orthogonal clearance, principal cutting edge angle and auxiliary cutting edge angle. If you have followed the sketch I have drawn on this white paper with the sketch pen, then you can simply match those values with the statement made here. So, we go to the next section. Friend, it is the normal rake system. Normal rake system is just an extension of the orthogonal system. Let me draw the figure once more. So, this is the cutting tool. This already we have drawn cutting edge. Now, we take the view on the cutting plane. So, if we take the view on the cutting plane, it will come more or less like this. This is okay. So, this is the main cutting edge, principal cutting edge. And how did you put the orthogonal plane? The orthogonal plane goes like this. This is your orthogonal plane. How do you define orthogonal plane? Recapitulate. So, this is orthogonal plane, that means this angle is 90 degree. Okay. So, the orthogonal plane, if I draw like this, it goes like this. It is your orthogonal plane, it goes like this. Okay. So, this is your orthogonal plane. Now, you have to get one normal plane, because now it is a normal rake system. You have already seen normal rake system, and to have a normal rake system, you have to erect one sectioning plane which should be normal to the cutting edge. So, this is the orientation of the cutting edge, this is lambda, already we have learnt it. So, you get this plane this way. So, that is actually the normal plane. So, let me have this color, with this you get this normal plane. So, friend, I request you to make the difference between this normal plane and this orthogonal plane. So, where is orthogonal plane? This blue one is pi o, and where is normal plane? This one, what I write with this red marker, that is pi n. So, you erect a plane which is normal to the cutting edge. So, if this angle is lambda, obviously geometrically that should be also lambda. So, what you have to do now, please notice one thing, we should not make any mistake here. So, this line should come and this surface, that means the surface confined by these 4 lines, I am showing, please mark it 1, 2, 3 and this is 4. This surface which is confined by these 4 lines, that is nothing but the principal flank. So, I am showing the principal flank, keep it in the upright position. Here the face is in the top view. Here you get the, it is turn, it is quarter turn and then you get the side view. So, how to get reasonably? So, you simply extend this line. That means you are sawing like this. You extend, you get a section and you do the same process. So, you get this line, you get again this trapezoid and wedge. So, this is the wedge. Friend, please note down that this is done at right angle to the cutting edge. So, you cut it and take the whole thing on this side, and if had it been your orthogonal, it would have been like this. Again this angle will be lambda. So, it is also possible, I have drawn one with black, another with blue. Another with blue. So, with that what I can show that this is actually, it comes on this comes alpha O, this is gamma O, this is alpha n, this is gamma n. Please have a look, because here we are taking the section keeping the flank in the upright mode. Here the top view, that you are looking at the top view, here you are looking at the flank. Naturally clearance surface will be at the top. When you get back to this figure, that rex surface is at the top, but here clearance surface will be at the top. So, from this you get two figure, alpha O, gamma O and alpha n and gamma n. So, with this drawing you can come to a very clear conclusion what is meant by gamma n and alpha n. So, only you have to tilt the plane on which you are measuring those angles by an angle of lambda, and this is normal rex system. This is actually the latest ISO system. This is most relevant to take care of the tool geometry in actual practice, because lambda should exist. Lambda 0 is a very rare case. In most of the cases, tool is provided either with a positive lambda or a negative lambda. Anyway, let us complete this exercise. Lambda, then it is gamma n, this is alpha n dash, and then phi 1, this is phi, then this is r millimeter. And let me show you one thing what I have drawn in this case, just okay, this one, this figure. So, friend, let us compare. This is something what we have already written, ORS system, lambda. Lambda is common, gamma O is replaced by gamma n, alpha O by alpha n, alpha O dash by alpha n dash. That means that is on the auxiliary flank, you can do it, and then phi 1 and phi remain same. Everything same, the order remains same, only one is taken on the orthogonal plane and another is on the normal plane. So, this way we have complete specification of these cutting tools, and in this case we have to see that this way finally how the tool should be specified. So, this is one complete statement for all the 3 systems of the tool specification. Now comes important thing, that the correlation between these two, and to have that we have to go to the concept of master line. So friend, this is one system to the other. I can show you one how to do it, and rest of the thing you can try. It is not very difficult at all. So let us try to make one sketch and to see how this can be done. Let us try. These are the interrelation. So you have the previous one set of interrelation, that is between ASA and ORS. I have already written here, and this one is the correlation between ORS and normal rec system. So that is for us to establish those relationship. Now comes important concept of master line. At least let us take one such case. Now what is meant by master line? You have seen that rec surface is not horizontal. There are certain cases where you can use a horizontal surface, say form tool, thread cutting tool. In those cases rec is 0, but in most of the cases, to facilitate machining or to protect the cutting tool, you have to provide positive brake or negative brake, as the case may be. Now if that should be the case, then it is clear that the rec surface and the reference plane, which happens to be the base of the tool, they cannot be parallel. So the rec surface is going to meet at certain zone or certain location with the reference plane, and since rec surface is a flat surface, isn't it? Is a flat surface. So a flat surface with the tool base, which happens to be also the reference plane, so their line of intersection would be a straight line. So it is very clear. So and this line of intersection we call a master line. So redefining master line for the rec surface is the line of intersection of the rec surface with the base of the tool or the reference plane. Let us see what we can do here. This is one such cutting tool, top view. Now just I draw one line here, and this line I call it a master line. But how to justify? Now to do this thing, what we have to have? We have to take another view, and on that we have to consider the projection of all the rake and clearance in various direction. So a master line will look like this, as if the rake surface is meeting the reference plane all along this line. Now we can do it this way. This is what I have just now mentioned. This is master line. But how to establish this thing? So you have to consider that rake angle in various direction, that is actually confined by this master line. Let us try how to show it. How can we show it? So from this point we simply take the projection. I am not considering the clearance angle. So this is the point in question, and this point is located at a distance of h above the tool base. Now here I have one point. Now if you transfer this point here, then you can find that should be the foot of this plane of intersection. That means from this side, if I draw one line, this should show the slope of the rake measured on the machine longitudinal plane. Logic is here, yes, thank you. So, logic is here that this is the intersection. So, if this is the point, that is the point here, and that is the foot of this perpendicular here, that is Q. So, Q is here, and this all the lines whatever I have drawn, that is on the reference plane. So, you understand this diagram, that is on the reference plane, and this diagram what I have just now shown, that is on the machine longitudinal plane. Now, this angle, if I draw the horizontal line through this, then this point you can transfer on this projection to get this point. So, logically this line should be the slope of the rake measured along the longitudinal plane, and by definition this should be gamma x. Similarly, if I see this thing on this side, you transfer the same point P, and it is the same foot of the perpendicular, that height is h. So, you transfer this point here and you draw this line. So, logically this should be the slope of the rake surface, and the point is intersecting the reference plane on this line, and this happens to be gamma y. So, when you have gamma y and gamma x defined, you can do the reverse of that. You get the point first here, you transfer this point here on this YY line. Similarly, here you transfer this point, place it on the XX line, you get 2 points, and with 2 points that is sufficient to show the line of intersection between two planes. So, here in summary, this is the trace of the rake surface shown on the longitudinal plane, and that is the trace of the rake surface shown on the transverse plane. So, it is simply transferring these 2 points here and say this is A, this is B. So, obviously this should be point A and this should be point B transferred. Now, this is in the ASA system. We can transfer this thing to the orthogonal system also. How do we get? Orthogonal system means here this is your orthogonal line. Okay, I can complete. So, this is your orthogonal line. So, friend, please follow this sketch carefully because drawing is important. So, I have extended 2 red lines. Similarly, you locate the point here. This is your point P. Then you draw another line with an intercept width of h. This has nothing to do, this is h. So, this is h. So, logically this line if you draw, this becomes C, and here you transfer this C here. So, this angle is gamma O. So, with this you can get all those points, that means A, B, C. These are nothing but point of intersection of the rake surface. This is rake surface, this one too rake surface, and this one too also rake surface. So, all these points which are on the line of intersection of the rake surface with the reference plane, those points you can only locate in one plane, particular plane, and all these have to lie on this master line, and from that you get this master line. Now, what we can do? We can correlate the relation between this gamma O and gamma x and gamma y. So, that relation, to have that relation, what we can write here? What is QA? That QA, so this is also point Q, this one is also point Q, because this is the foot of the perpendicular. So, foot of the perpendicular should not change. So, QA is nothing but h cot gamma x. QC is H cot gamma O, then QB, that is H cot gamma Y. And if I now put H is equal to as 1, then this becomes intercept becomes cot gamma x, this is cot gamma O and cot gamma y. So, finally, this intercept PA, PB, PC, those things can be represented as cot gamma x, this is cot gamma y, and this one as cot gamma O. These three intercepts are the most important thing in understanding the concept of master line. Thank you so much for being with us. Well, we come back to our session and we have to complete our pending work. So, friend, where did we adjourn? It was this diagram, and we have found what is the significance of this ABC. Now, we can extend this diagram by this. I draw one line, transfer this, and this line is perpendicular to the cutting edge. So, it is transferring this point P and then just get an intercept having the distance h. It is looking from this side. So, it will be an inverted image obviously. Now, here we get one point A, B, A, C, we put it D. What is the significance of this D? This D is nothing but intersection of this cutting edge. Of course, it is extended, it is the extent of the cutting edge is between this point and this one. If you extend with a thread or with anything, it is going to meet the reference plane at the point D. So, how to locate this point D here? So, simply transfer this point D here, D, this is D transferred on this diagram, and from this if I drop it, join these two, I get this orientation of the cutting edge, and by definition all of us know that this is lambda. And friend, where is Q? This is Q as usual. So, you can find same Q on the longitudinal plane, Q appearing on the orthogonal plane, Q is very much on the y plane, and now we find the same point Q on the cutting plane or the tangential plane. So, finally, our statement is that this ML is created by identifying point of intersection of the rect surface in a particular direction, and it is happened to be A, B, C and D. And when we put it here, we get this master line. And why we call it master line? Because it gives solution to any problem concerning the geometrical feature of the cutting tool, I mean the rake. One interesting thing, you see gamma x, gamma O, gamma y or lambda, their magnitude will keep on varying because of the intercept. So, finally, this is the point P, but actually we are considering the point Q, because this triangle, the line that is on the horizontal plane. So, it should be Q just below P. So, it is P upon Q. So, it is actually the, if we consider the triangle formation A, C, B, D, that is one line, and then D should be joined with Q. That means, this D is with Q, Q is with A and something like that. So, finally, we get this triangle, and from that triangle we can develop this correlation. So, one correlation is, I am showing one how to do it. You can definitely try. Tan gamma O is equal to tan gamma x sin phi plus tan gamma y cos phi. How to arrive at that? If we understand one, we can do. Now, friend, it is, there are some little trick. So, gamma O is to be determined, and that is in the center. So, you consider this part of the triangle A Q B. with C as an intermediate point, and there what we find? We find two triangles, actually it is three triangles. One is triangle A B Q, and what is the area of this triangle? This triangle is half AQ into half QB. So, what is AQ? AQ is cot gamma x. So, it should be cot gamma x into cot gamma y, straightforward relation, and that should be equal to how much? You divide it into two triangle. Triangle ACQ is equal to triangle ACQ plus triangle BCQ plus triangle BCQ. Okay. So, friend, we get back to the properties of triangle area. That means, if it is ACQ, in ACQ we know two sides AQ and QC. AQ is known, QC is known. So, it is cot gamma x into cot gamma O into sine of angle between these two. So, you have to find the sine of angle between these two and then put it this way. So, it will be how much? This angle is phi. If this is phi, then this angle should be also phi. This angle is 90 minus 5. So, it is not at all difficult. So, for triangle ACQ, what you have to find out? It is half of cot gamma x into cot gamma O into sine of angle between these two, and this happens to be 90 minus 5. So, you put sine 90 minus 5 plus what? Triangle BCQ. So, BCQ is half this into this, two sides and included angle. So, one side is QB, another side is QC. So, what is QB? QB is cot gamma y, putting h as 1 we have already mentioned. So, it becomes cot gamma y into cot gamma O as usual, that is the common, and there the included included angle is sin phi. So, if you put, it is just one line derivation you get at, and following this, friend, you should be able to do all the deductions, and let us review once more the deductions. Okay. So, before that we have one more. Yes, this set. So, I have shown how to do it, and all the thing you can do. If you have any problem, you can get back to me over mail or any way you can talk to me, no problem. It would be my pleasure to help you as far as possible for me. So, please try yourself and find the pleasure in handling those problems. So, friend, now one thing should be understood. So, this is actually master line. Okay. So, let me draw one fresh picture. Already it is clumsy. This is cutting tool, and if we place the master line, this is phi, we can immediately recognize phi 1, and this is a master line. So, what we have to do? Reasonably select one point, and from that point we draw intercepts. This is in y direction, this is in x direction, it can be outside, no problem. This is somewhere here, and this is this way. So, logically this is cot gamma y, this one is cot gamma O, and this is cot gamma x, and this is cot lambda. So, this line is actually cot lambda. So, this intercept is cot lambda. Anyway, now from this one observation we can make, that if we drop from this point one line which is perpendicular to this master line ML, this is master line, this intercepts has the minimum value, because the perpendicular distance is the minimum. Obviously, our logical conclusion would be, along this direction the slope of this rect surface that is the highest. So, along this direction you get gamma maximum. This gamma maximum will be normal to the master line, and by the same logic along the master line, in the direction of master line, rake angle will be 0. So, it is coming from cotangent. Cotangent minimum means your angle is maximum. Cotangent, when it is along this line, that gives you a 0 angle, and here we have another angle phi gamma. So, this phi gamma is nothing but orientation of the master line, the way you define the orientation of the cutting edge phi. Now, you define the orientation of the master line in the direction of x direction. So, friend, with this as, so this intercept would be how much? This intercept, if we have chord gamma, so by the same logic this intercept will be chord gamma max. So, just it is some trigonometrical manipulation. With that manipulation you can simply arrive at those results. Okay. So, it should be here. Okay. Okay. So, this is one relation. So, you have to follow up, and this is for the normal to orthogonal, but this is very important. That means it comes as a square. So, you see it is almost like a circle, and this happens to be your radius. So, it is radius square is equal to x square plus y square, and this is also x square plus y square, because you have two transverse axes. It is either this transverse or it can be like this. It can be either like this or it can be like this. These are the two transverse axes, and here along this you have the radius. So, with this radius it is possible to deduce this relationship. So, friend, this is something interesting, and one can try to establish, and from there you get a circle which gives you all the relationship based on the circle. But however, it is to be reminded that master line, it is the like your master key, it gives solution to. That means in any direction, if you draw any line, you keep on drawing line in any direction. What does it mean? This direction you have some intercept. Here you draw one line, you have some intercepts. This intercepts is nothing but cotangent of the slope of the rect surface along this line. So, if you like to choose any direction, you can immediately get to know what is the rake angle simply by on a scale. You scale out and you measure this on that scale, and you know what is the cotangent value, and you convert it into degree. So, with this point in question and getting the orientation of the master line, you can know all the angular feature of this cutting tool on the rake surface. Okay, friend, it is tool in use system. Now, in tool in use system, you understand one thing, that when you have a cutting tool, okay, a cutting tool in use system, it is just to give you some idea of this. This is a tool in one plane, and this is say rake angle, and this is clearance angle obviously. However, these are all in tool in hand system, but here you have the direction of velocity Vc, and here you have a feed velocity Vf. Now, with this what happens, your resultant velocity changes, and your resultant velocity direction assumes this direction. So, this is Vr. Now, when it is Vr, you have to extend this line. So, in this case the reference plane is not parallel to the tool base, it is actually parallel to the velocity vector. So, as I have already mentioned at the beginning of the lecture, that in tool in use system you have to consider the resultant direction of the resultant cutting motion and the direction of feed. So, in this case Vc Vf, when you compound it you get this Vr, and with this Vr you get the reference plane pi r. That means here we change the definition of this reference plane. Reference plane is a plane which is always perpendicular to the velocity vector, and it is very relevant in case of your tool in use system, because now it is a working tool. So, originally this was the reference plane, this was the cutting plane, but now this is the reference plane. So, originally this was the rake, now this is the rake. Similarly, originally this was the clearance, but since the direction of BC has changed, this clearance angle is small. So, friend, this is also another thing one has to look in when you have the tool in use system. Because of the direction of velocity, those static angle or which are used in tool in hand system, which is good for grinding of the tool or for sharpening of the tool or just for nominal designation of the tool, they may lose their relevance when you talk about the tool in use system. So, friend, these are the two references Boothroyd's Fundamentals of Metal Machining and Machine Tool and A. Bhattacharya Metal Cutting Theory and Practice. These are for your immediate reference, and that will be very useful for advancing your studies. Okay, now we go to the next section. These are the some of the quiz you can try, and if you have any difficulty then get back to me, but these are something based on your concept. Here I have not said anything where you have to memorize complicated very big formula. From your concept you try to understand, try to answer. No formula. In fact, in those cases you should not use any formula mechanically. If you use mechanically the formula, your idea will not be clear. From the diagram, so far we have drawn so many diagrams. Based on those diagrams you try to answer, otherwise you can get back to me. Now, friend, it is mechanism of chip formation. Ultimately, the geometry of the cutting tool means mechanism of chip formation with ease, not with difficulty. So, how this chip gets formed, what is the inside story, that we have to understand. And here factors influencing the chip, characteristics of the chip. What material? You know, mild steel, cast iron, aluminium or graphite, they are varying. Brittle, very brittle, ductile, very ductile. Then type of cut, continuous turning or milling. So, this is one example. Cutting tool material and geometry, high speed steel, carbide or ceramic. Geometry means positive rake or negative rake. So, these are the few issues are there. So, based on that you have to understand that this can make the task which would have been otherwise very easy, but because of the lack of knowledge, lack of understanding, poor selection of those parameters, your task becomes difficult and almost impossible. Machining parameters, speed, feed, depth of cut, definitely they do matter, and ultimately last but not the least, dry cut, wet cut, if it is cutting fluid, how you are applying, what is the chemical composition, it is a jet, flood or mist, atomized, lot of things are there. Chip as an indicator of what? From the chip you should be able to tell about making some impression, that type of work material, ductile or it is partially hardened or it is really hardened. It is the mechanism of chip formation. We shall look into brittle fracture or say yielding, shearing. We talk about shear deformation, we shall take up. Level of cutting temperature. So, chip color is a good indicator of this cutting temperature. It is metal luster having little yellowish, blue and yellow combination, deep blue, deep black and so on. Then condition of the cutting tool, from the chip formation you can tell rake angle, is there any edge built up, geometry has modified, changed because of the tool wear or breakage, that also will be indicated by the type of chip. So, an expert would be able to judge or make a good prediction that yes, the chip shows that there is some problem in your machining. So, please inspect the whole thing simply physically looking at the chip. The cutting tool influence of cutting parameters, that is also indicated by the chip, proper selection has been done or no. Then cutting environment, dry, you can change it to wet, wet means what type of. So, best type of chip we understand if that is your reference. So, if you are away from the ideal one, definitely you are in a position to make those observation and remarks, and corrective measures has to be taken. Friend, this is something interesting, very fundamental. We have our own experience, ductile material, how it undergoes deformation and removal. Finally, it is removal, separation. You have to physically separate it, that is very important, and either it is by shearing plastic flow or by brittle fracture. Best example, you put mild steel on one side and cast iron. These are the two material we are very much familiar with these two material. Even in our day to day assignment or workshop practice, we have handled these two materials, not others, but at least we should be able to differentiate between mild steel, low carbon steel which is ductile, and cast iron which is brittle. So, these are the two ways how they ultimately separation of the chip from the parent body takes place, one by brittle fracture, one by shearing. Now, these are the classification of the chip. You have cast iron irregular chip, continuous chip means a right condition, you have endless chip which may create a problem in handling the chip. So, somewhere you have to break the chip intentionally. Now, you can also have continuous chip with built up edge, that means on the tip of the tool you have a material get stuck on that, and that comes from the work material, still you can have a continuous chip. Element chip means in certain condition which depends upon selection of the cutting parameters, selection of the geometrical parameters, selection of the environment, and if these are not favorably chosen, in that case what happens, a material which by the law of nature should have given a continuous chip, that becomes a discontinuous interrupted chip, and it shows cutting is not favorable. That may also happen. You have partially continuous chip, it is in between continuous chip and element chip. So, these are the type of chip you can get into any reference book or textbook, you can see it. Now, friend, comes the chip reduction coefficient. So, let us look into this. What is chip reduction coefficient? So, it is a classical way of understanding the cutting process, classical way. If you know Pispanen's model, that would be an idealized model. Nevertheless, that is one of the very basics of our understanding the chip formation mechanism when it is a ductile material. So, let us draw one cutting tool having this shape. So, here I put the clearance angle, this is the material, and here this is the chip. So, this picture is so common anywhere in any book or any explanation, we cite this one. So, this is the velocity vector. So, tool is moving in this direction V c, and we have two more parameters. This is rake angle, this one we call it, I put the symbol A1, thickness of uncut layer, this is called thickness of uncut layer, and this is actually the thickness of the chip, which is A2. This part is chip and this is uncut layer. And what happens? Here you have diversion. it is not only diverted, but it gets thickened, and that is exactly what we talk about, this what we call chip reduction coefficient. Now, if you have length of the job as L1, so the tool starts from here, that is the initiation and that is the termination, that is the length of the uncut layer. You have thickness of the uncut layer, you have also width of the uncut layer, that we cannot show because it is 2 dimension. It is a cutting tool, you recall a shaping tool having the cutting edge length sufficient length perpendicular to this plane of the paper. So, this is in the process of machining, removing this layer. Now, in this process what we can find, that L1 A1 into B1 is equal to L2 A2 into B2, and for the moment we consider it as a idealized situation where there is no side flow of the chip, no widening of the chip, it is absolutely 2 dimensional cutting, and with that what we find, that L1 by L2 is equal to A2 by A1. Okay. Now, further to this, if you consider the material removal rate, from that also you can have replacing, you have the cutting speed, you have A1 B1, that gives you the material removal rate, and then this is the chip is flowing with a velocity Vf, and then this is also Vf A2 B2, and we consider that B1 is equal to B2 considering 2 dimensional orthogonal cutting. So, from this 2 cancelled out here as usual, we also get Vc by Vf is equal to A2 by A1. Now, friend, this ratio Vc by Vf is equal to A2 by A1 is equal to L1 by L2, this we called chip reduction coefficient, because chip length is contracted, there is a contraction in length of the chip. This is a small experiment you can try yourself in your laboratory or workshop, having such a rectangular piece of this size of this is actually B, and you have a cutting tool. So, this is L1. So, you can, but only the question that you have a continuously flowing chip, there should not be any breakage. With that you can really establish that L2 is less than L1. So, friend, this contraction means that we call chip reduction coefficient, and this chip reduction coefficient we call it an index of machinability. Performance of cutting tool, machinability of the work material, performance of the cutting fluid, proper choice of cutting parameters, especially Vc or rake angle, all these things, whether it is good or bad, proper or improper, that will be simply very handy way of judging your machining performance by this ratio, and this you can even measure the thickness of the chip with a point anvil micrometer, and it can be a very interesting experiment, changing the rake angle, applying the cutting fluid. So, this way we understand chip reduction coefficient. Okay. So, we have we have explained chip reduction coefficient. Now, we go to one more how this chip reduction coefficient is influenced by the tool material. That is one important point. Tool material, if you may I have your attention in this equation, we use the symbol zeta for chip reduction coefficient, which already we have defined. A2 by A1 is equal to L1 by L2 is equal to Vc by Vf. Now, this is also expressed in terms of e to the power mu into pi by 2 minus gamma. This is known as a famous Cronenberg's equation. You can find it any textbook, Cronenberg's equation, very important equation for explanation of this metal cutting phenomena. Now, what is mu? Mu is actually the chip tool interface friction. Okay friend, can we go here? So, this is chip tool interface friction. So, that is mu, and we get back to again here. So, that is mu, and what is pi by 2 minus gamma? That is actually diversion angle. This is the diversion angle. So, here we can see that this is the diversion angle, and this diversion angle is actually let me write pi by 2 minus gamma. So, if you have this as gamma, then pi by 2 minus gamma, which is known actually cutting angle, this we call also cutting angle, and you can find this is denoted by the symbol delta. So, this is the rake angle has an influence and mu has an influence. So, we can combine the effect of this coefficient of friction at the chip tool interface here. No, I like to go to that. So, friend, here so this is the chip tool interface friction, this comes here, and then this is the gamma. Higher the positive value of gamma, more will be chip will be directed in this direction. You have a low value of zeta. Higher friction means high value of zeta. So, you must reduce the coefficient of friction obviously, and a favorable high value of gamma, that also helps you in getting a low value of zeta, means less deformation and ease of chip formation. Okay. So, what happens now comes what we call shear angle. So, let us try to understand. It is an idealized model. First of all, we have to know this is an idealized model, and here we can bring this great name idealized model. Chip formation during machining of, in case of ductile metal, in case of ductile material, say mild steel, low carbon steel. So, the idea is like this. This is your uncut layer, and here you have the separation. So, we know this is gamma O, orthogonal rake. Okay. So, this is A1 obviously, this is A2 chip. Now, what is considered that this is a shear deformation process. So, when the tool moves in this direction, it is actually compressing. Now, because of this external load, the entire material ahead of the cutting tool will undergo deformation. So, there will be stress development, and this stress can be resolved in any particular direction into two components. One will be tangential to that plane, another will be normal to that plane. And interestingly, in a particular plane, that induced tangential stress exceeds the shear strength of the material, and the material follow a preferred path of shearing. So, that is the whole idea of this idealized model of shearing. External load, internal stress, stress is resolved into two planes in any direction, one normal to that direction, one is tangential, and in a particular direction the tangential stress exceeds the basic shear strength of the material, and material fails by shear. And it happens to be, in this case, by way of illustration, that this happens to be that shearing direction. And you know, in a ductile material you have crystallographic planes, slip plane, slip direction, you have FCC material, you have BCC material, each has its own slip system. one slip plane and slip direction. So, those things definitely comes in the picture. Anyway, this is the shear direction and what we consider material ahead of the cutting tool, this we consider like a series of a stack of undeformed material. Okay. So, as it comes over here, it is not allowed to move on this side. So, it will be halted, and what will be its position as it moves? So, it will take up this position. So, this will be the position. So, this is one layer which is moved by this cutting tool action. What was one just before that? You can draw like this. You have series of those. So, friend, in summary, this layer before cutting it has such orientation, and just after this deformation it takes this course and it moves like a part of the chip. So, this is in the uncut layer and this is now an integral part of the chip. So, where is the shear, friend? To know that, you have to consider this thing. In the absence of the cutting tool, had not been there, what would have been the position of this point? This point would have been here. Now, the tool was here. Now, as the tool is moving, this point is shifted. Try to understand. Let me draw a bigger picture in this way. That means, if I consider this is the point A, this is A, and the cutting tool has shifted the point A, it is pushing by shearing action and it is shifted to point B, and you have a layer on this side. So, and what is the thickness of this layer? This is the thickness of this layer. So, here this is the thickness of this layer. So, you drop one perpendicular, that is the thickness of this layer A B, and this is a point say O, and you drop a perpendicular D. So, friend, finally it comes to that this each layer is undergoing a shear deformation, and in the process A point, this whole thing, it was here and it is sliding, slipping, and in as a result of that, this point is moved here and it has two velocities now. Originally it was Vc on this side, but from this you have two velocities, this Vc. From this Vc, two new velocities appear in the scene, two component. One is the shear velocity, this is shear velocity, and now this is the chip velocity. So, this is the shear velocity by which it is shearing and it is also moving in this direction. Now, in this process, what you have to see, it is the movement from A to B by shearing action and over the length OD. So, what is your shear deformation? Shear strain? Shear strain will be nothing but AB by OD, AB by OD, and this AB can be also splitted into AD plus BD by OD by OD. So, you split it into two triangles, one is this one is this beta and another is this small one beta minus gamma, and it is just one line trigonometrical manipulation. From this we can write immediately it is cot beta plus tan of beta minus gamma. So, from this we get to know that this is actually the shear strain. Obviously, you understand by apply our common sense, the shear strain with minimum shear strain we have to get the work done, and for that the tool geometry, cutting parameters, these have some role to play. Metal cutting, shear strain is very high, strain rate is also very high. It is just not your material testing, what we do is the shear, it is the cutting strain, and strain rate is extremely high, and that is why this is quite different from classical shear deformation. So, friend, this is actually shear angle and shear deformation. So, shear angle I have shown that this, okay, I have to go to this diagram. No? So, this is actually your shear angle, this whole angle, that is shear angle. So, smaller the shear angle, poor machinability, larger the shear angle, better machinability, good machinability. Chip reduction coefficient low, good sign, high is not that favorable. Now, we have to quickly go to this one. So, this is cutting strain, we have already mentioned cutting strain. I have written already in the paper cot beta plus tan beta minus gamma, and you can find out, it is not difficult, that how to get the minimum value of the shear strain. So, what you have to do? What you have to do? You simply get the derivative of this one with respect to zeta. You get the derivative of this one with respect to zeta, and you put that derivative is equal to 0. From there you find that zeta has to be equal to 1 to get the minimum value of the shear strain. It cannot be less than 1, but theoretical sake, if it is less than 1, it should be also, it won't attain the minimum value, it will be higher than minimum, and always zeta is high, obviously this cannot assume the minimum value, and from that you get a relation shear angle and rake angle. So, this is another important relationship, in that significant that cutting task has to be made very easy, favorable, and for that what are those needful we have to do. So, friend, with this we come to the reference, and these are the two books, A.B. Chattopadhyay and A. Bhattacharya. These are the two books you can see. However, I can mention one thing, that effect of zeta with Vc, okay, or effect of zeta with rake angle. So, what happens, and you have different value of feed. So, it goes like that. I have drawn 1, 2, 3, 4 curves. Now, you change the feed, this is cutting feed, it is zeta. So, that means on this side what you have, feed value is increasing. So, here you write feed means feed value is increasing. Say this is 0.1 millimeter per revolution, this may be 0.2, 0.3 and 0.4. What you can find, that this value of zeta will be less with high feed value, and it will be more with low feed value. So, this is one important observation. With increase of Vc, you can favorably reduce the value of zeta. Similarly, with gamma you have this value of zeta. So, this can also fall, and with increased value of zeta. So, this is increased value of rake angle. So, here you have high value, but as you keep on increasing the, this is actually, sorry, please correct it, this is actually A1. A1 means it is the uncut layer. Already what is uncut layer I have already shown you 5 minutes. Okay. So, friend, this is A1. So, please correct it in the drawing. So, this is A1. So, with increase of rake angle, what we find, that the zeta value will keep on changing, and this hump is also gradually disappearing. So, this is also one important observation, and this can be explained by the formation of built-up edge, and this built-up edge is promoted by pressure and temperature. So, when you have high value of A1, temperature is so high that it cannot get frozen there, and that is why you have a low value of zeta and no hump. And with rake angle, obviously that answer is already given. If you recall Cronenberg's relation, from there you can get this value of this observation. Another thing, that this value of zeta with rake angle, we know rake angle is 0 here, this side is negative and this side is positive. So, you put the chip reduction coefficient against rake angle. So, what is our common observation? When the cutting tool is having large negative rake, that means it is from the tip of the tool, it is sloping upward. This is negative rake, this is rake is equal to 0 and this one positive rake. Now, it is our observation that with this it falls like this, but you can have a change in the pattern and finally, it becomes almost horizontal. This side it is high value, this side it is low, and this side it is VC. Say you have 100 meter per minute cutting velocity, 200 meter per minute, and now it is 300 meter per minute. So, it is also one observation that when we have very high velocity, rake cannot influence zeta, or so to say that if it is a tool with negative rake, obviously zeta value cannot be favorable, particularly with carbide, coated carbide or ceramic tool. So, what you are going to do? Where is the solution? You have the option to increase the speed to very high value, 300, 400, even 500 with those tools. It is not 300 to 600, 30 meter to 60 meter per minute, as it is the case with HSS. So, for HSS, when it is a low speed, you can also have a curve almost like this, very high value with negative rake at the low speed end, but when it is a high speed, the advantage of this cutting tool material can be exploited and zeta value you can get to your advantage. So, friend, this is one discussion we have already made, and can we conclude now? Okay, friend, some of the interesting questions are there. You try to handle those, and from your understanding you should be able to respond to this, but if you have any doubt, any further clarification, you can get back to me. Okay. So, here I find one question.
I see. That you have told NRS and ASA and ORS, among those which is preferred one for a basic metal cutting operation?
You mean the ASA and ORS?
And NRS.
NRS, okay. Okay, friend, finally, look, these are the three things I have already mentioned. ASA was actually came into being the first, and later it was realized that this system has some limitation. So, then you have orthogonal rake system, which is actually the German system originally. However, later it was also found that the very existence of lambda should be also considered, and when it is the case, then you have to finally consider the normal rake system in your all analysis, but it becomes then a 3-dimensional problem. When it is orthogonal machining, we call it a 2-dimensional problem, because we do not consider any deformation or flow of the chip in the direction of the width. We consider only it is the thickening of the chip, we do not consider it is widening of the chip. But when it is the real life machining, it is the real life tool. So, in that case definitely it is the normal rake which comes in picture. However, to start, we start with a very simple problem. So, if it is the problem of machining, so you have to check the suitability of a cutting tool. It can be material, or it can be workpiece, or it can be selection of cutting velocity or feed. So, in that case, instead of taking a 3D issue, you take a 2D issue making lambda 0 and you choose those parameters in such a manner that the chip flows along the orthogonal direction and it does not get deviated from the orthogonal direction. So, with that you can generate lot of information which will be useful for taking your strategy in actual practice, not only in laboratory or workshop, in industry. However, I must add again that in real life situation the lambda has to exist, and with that lambda definitely the problem of machining becomes a 3-dimensional problem.
Good afternoon, sir.
Yes, good afternoon.
Sir, we use master line to get angular feature of cutting tool.
Yes.
To get angular.
Yes,
Sir, hello, sir.
So that
We use master line to get all the angular features of the cutting tool.
yes.
Is it only one purpose? Is it only one purpose of master line?
Okay. So, is your question statement is over? Okay. Now, getting back to your question, master line, whatever I have shown, that one in detail, that is for the rake surface. You have actually 3 master lines because you have 3 surfaces. First one is the rake, second one is the principal flank, and the third one is auxiliary flank. So, what is meant by master line? It is the intersection of the plane which is a real life plane of the cutting tool and which intersects with the reference plane. So, when you consider the principal flank, you have one more master line, and when you consider the auxiliary flank, you have the third one. So, the master line for the rake whichever I have shown, with that you can find the rake angle in any direction. But if you like to know the master line, if you like to know the clearance angle in any direction, you must use the master line for the principal flank. Following the same logic, if you like to know the clearance angle in any direction of the auxiliary flank, then you must also consider the master line for the auxiliary flank. That is the thing. Friend, this could have been covered, but we are also limited by our time. Otherwise, had you been here physically, it would have been a great pleasure for me to give those explanations. Is that answer to the question?
Tool nose radius has to be different for different turning operations.
Tool nose radius, yes, and then
Has to be different for different turning operations.
Okay, friend, tool nose radius has so many things to do. First of all, immediate effect is on surface roughness. You know, surface roughness is given by the well known formula S square by 8 r. What is r? R is the nose radius, S is the longitudinal feed. So, immediately your conclusion is larger the nose radius, better will be your finish or lowering the surface roughness. However, to strengthen the cutting tool, you have to also put some nose radius. For example, for carbide tool, you have to have a liberal nose radius. It cannot be just like your high speed steel, where you can have almost 0 nose, may not be 0, almost 0, but for carbide at least you have to give a nose radius, say for example, which are available of the shelf 0.4 millimeter, 0.8 millimeter, 1.2, even more. It depends upon the intensity of cutting, that means heavy cut, high depth of cut, high feed. This is one to protect the tool against possible fracture. However, you cannot do that in an unlimited manner. If you keep on increasing the nose radius, you can see tomorrow in lecture I shall try to explain this thing, that the radial component of the thrust force will also keep on rising. That means in the transverse direction, and that may cause a great damage to the workpiece roughness. There can be vibration, even that brittle cutting tool, its edge may undergo edge chipping edge breakage. This is one issue. Third one is temperature. You understand, cutting point temperature is one of the determining factor in holding the life of the tool or its service life. So, in that case it is also understandable that if you put wide nose radius means you put extra mass, and extra mass means with the same heat load you can bring down the temperature. So, with that, if you have a judicious choice, you can definitely get a benefit by providing a nose radius, and definitely from material to material where you expect large force, tool is not that strong in tension, you have to put nose radius. Where you find tool is tough and there is no such risk of tool nose breakage, you can do away with nose radius. Obviously, a sharp tool for rough cutting, that will be useful, but when you come to the finish cut, in that case material removal rate is not the big issue. You have a light cut with fine feed, but very high speed. So, in that case a wide nose radius will definitely help you in getting a good finish.
Hello.
Hello.
Good afternoon, sir.
Good afternoon.
Sir, how does if there is an effect of moisture present in the environment on the machining parameters or the chip formation?
Which one? Effect of?
If there is if the moisture affects the machining process.
What affects? I couldn't get the first word.
Moisture. If the moisture affects the machining process or the chip formation process.
In the chip formation process, that I could follow correctly from you, but first part of the sentence.
Sir, moisture, atmospheric moisture.
Atmospheric moisture. You mean moisture?
Yes.
Moisture.
Yes.
Okay, okay. Now, in that case, what happens? There are certain cases where this atmospheric moisture can increase the friction. So, in that case definitely force may rise. So, it is the moist or dry air that may matter, and if it is under vacuum or with argon atmosphere or with oxygen, definitely you can control your what we call the cutting force. Say if you carry out the whole operation under argon atmosphere with a carbide tool, force will rise. But if you apply little oxygen in normal atmosphere, force will come down because of the oxidation, and oxidation at the chip tool interface, that reduces the friction, and that is proved. It is true in that pair, that carbide tool as the tool and mild steel as the work material. You carry out one experiment with a high concentration of argon, and in one case you do not use argon, and you can check it on the in terms of cutting force definitely. Any other question? Corrosion, yes.
Corrosion.
Corrosion.
Corrosion over the metal surfaces.
Okay, okay friend, it is obviously if you have a cutting fluid, the choice of the cutting fluid is definitely important in that it should protect your workpiece. So, if the cutting environment cannot protect your workpiece, definitely there will be corrosion. So, you have to look into what are those agents present which can attack the nascent surface. Are you getting my point? When you machine the surface, that is absolutely nascent and virgin surface. So, attack will be severe. However, there is one point. If you consider two surfaces being produced under the same condition only with change of feed, you do not change anything, only change of feed, means one will be smooth, another will be rough. Are you following? One will be smooth, another will be rough. You keep those things in your workshop or laboratory for 7 days and you come after 7 days and see the attack on these two. The surface which is rougher, that will be attacked severely than the surface which is having a shining mirror finish. It is because of the sharp points. those are acting like galvanic cell, and it is you know, engineers, we understand a sample which you need to preserve, you should keep under vacuum, not in open atmosphere, isn't?
Means vacuum environment is maintained, sir, while machining.
You can maintain, no problem. Nowadays you perhaps you will be it is amazing to know that you need the tool where under an electron microscope, okay, microscope. So, within the microscope the cutting can be conducted, and that electron microscope is put under vacuum. So, under vacuum you can conduct the cutting, no problem, but you must have that facility. Either it need not to be ultra high vacuum, but a medium vacuum or a low vacuum, you can definitely do that. Only you have to have one spinning machine, a lathe, small lathe, why not? Any other any question? Friend, have you followed the master line,
No,
concept of master line?
No, sir.
No, why not? You
Yes, sir.
you look into this, okay? You look into
Yes,
this.
sir, I have followed.
You no, you look into this time and again. This is you understand. I mean, this is your first introduction. You go through that, and this master line, as I have said, master line is like a master key. What is meant by master key? With that key you can open all the lock. No, it is said, it is a proverb. So, master line means with that line you can find out the angle in any direction. That is the master line. It is a master, master means expert. So, it is a master line. So, you can determine the angle, say master line for the rake. So, with that you can find out. Okay friend, just for recapitulation once more, since you are here, if you have patience then perhaps I can continue. আপনাদের কোনো booking নেই তো? Okay friend, you have to follow first this diagram. Okay, it is complicated. I have drawn it here, I have drawn it, prepared it here in your presence. I have not brought anything already prepared. So, I have prepared this thing in your presence. So, each stroke you can understand. Friend, only the thing is that here please have a look, point A, B, C and D, significance of these 4 points. So, with these 4 points you can have the line of intersection of the rake surface with the reference plane, and that is why we call it master line. And with this master line, for this point P in question or under consideration, if you draw the intercept from this, you get the cotangent of all those in any direction. So, if I draw one line, say for example like this. So, in this direction, this one in certain scale, that should represent cotangent of that angle. So, if you know that value, numerical value, you can get that one. So, that is exactly the master line. So, that is the idea behind it. So, you need not memorize any formula. So, with that you can find it, that is the whole issue. Have you followed maximum rake, concept of maximum rake? Please follow those slides, okay. There are
Yes,
many things which are typed, already typed available. So, those equation, that is the maximum rake. Now, when you examine a tool, you have slope in every direction, no, gamma x, gamma y, gamma o, like that. But you must be able to find out that in a particular direction the rake is maximum, but that is not, neither it is gamma x, gamma y, nor it is even gamma o. Maybe it is another direction. So, question is, if you are asked to know, tell along which you have the maximum slope of that surface. So, what will be your response, or how do you proceed to get that direction? That is shown here. So, you discuss with your friends, you yourself think over. Friend, look, one thing, I have made few strokes, no.
Thank you, sir.
It is not a description, it is not write an essay on master line, okay. It is not a description, write 10 lines on master line. It is simply conceptualization of the whole thing, okay. That is it.